Hey out there, OTB Labs guys and girls in isolation. Welcome back to our weekly live stream, and today we're making crystals. Crystals are pretty cool. You can make crystals out of so many different things in your house, and as we mentioned last week, since this is being recorded as it's streaming, you can go back and watch this and do it again and again and again with all manner of different stuff that's around the house. Pretty much anything that dissolves in water is going to be something you can use to make crystals out of. So some of the stuff we put in the materials list, I'm going to just run through what we have in case you have it or you want to grab it real quick. I have magnesium sulfate, which is Epsom salt. That's used as like a foot bath or a foot soak for sore muscles. That stuff usually found in the pharmacy section of a grocery store. If you don't have it and you find it later on, you can make crystals with it. Regular old sodium chloride, a lot of you will know as table salt. Makes really, really awesome crystals. We're actually going to get an up-close look at those tonight. Borax, sold as a laundry detergent or a laundry booster. It's just a flaky white powder. Makes pretty cool crystals. You can find that stuff in the laundry section at your local grocery store. And this stuff here, sodium Meta Bi-sulfate, or sulfite rather, this is sold as a stump out or stump remover in a lot of hardware stores. It's a white powder as well. That will make cool crystals. Maybe have some of that in the shed or the garage. Another one you can find at the grocery store which makes really sweet crystals called Alum. This stuff is sold in the spice section at just about every grocery store. And this stuff makes very nice crystals. And then if you have a pool or an aquarium, you might have some of this blue powdery stuff. It's called copper sulfate. It's actually also sold as a tree killer or a weed killer. So I think it's sold under the brand name Root Kill. If you have some of that in the shed or in the garage, or you happen to pick some up later, if you don't have it, that'll make really, really, really cool crystals. Now, just a quick reminder, we are still taking submissions for our Rube Goldberg Challenge, and you can find information about that OutsideTheBoxLabs.com. You can also find our DIY side kit. And if you have the DIY side kit already, I know a lot of you do, you want to get your hands on your little Petri dish because that's going to come in handy tonight. A lot of you have that on the way, again, being recorded. When you do get it, go back through. A lot of the stuff that's in that kit will be helpful for what we are doing this evening here. Now we're going to get right on into the crystals, and the first question that we ask when we do this in schools usually is, what is a crystal? And we get all kinds of really, really interesting answers from the students. And people tend to think of like diamonds as a crystal or gems of different kinds. And we pass some stuff around and say, is this a crystal? Is this a crystal? Just to get you thinking, because crystals come in all different shapes and all different sizes. But the key to what makes a crystal isn't, is it pretty, or can you make jewelry out of it? All sorts of matter will crystallize, and the real key to what a crystal is the shape. I'm going to actually show you, maybe I'll bring this up close unless Sarah wants to come close, a couple of alum crystals. These guys, you'll notice here's a little one, and here's a big one, and the key is the shape, and we're going to get into why the shape is the key. You notice this is kind of like a six-sided, sort of a hexagon with another hexagon, and they're twisted. It's a three-dimensional shape is the key to what makes a crystal different from something that is amorphous or non-shaped in Latin, that's non-crystallized. We are going to take a look tonight at a bunch of different types of crystals, but one of the types of crystals tonight that we're going to look at is edible. Now, only one type of crystal we're going to make tonight is edible, so I want you to pay close attention to me as we're walking through this. About to pull out the microscope here and take a look at something, but first I want to show you crystals from this blue powder, the copper sulfate, the stuff I said you can use as a pool cleaner or as a root killer. These are what the crystals look like when they are fully grown and finished. This is a really big one. This is a little smaller one yet, and a very long skinny one. But you should notice these are all sort of parallelogram shaped pyramids. No matter how you turn it, it's a parallelogram. And again, the shape is key here. This is another copper compound. This is copper acetate. I made the copper acetate myself. A bunch of little copper acetate crystals stuck together. Here's a bigger one, and again, they're kind of parallelogram prism shaped. Parallelogram prisms. Now we're going to take a look at these copper sulfate crystals through the microscope. Now again, I said no matter what way you turn this guy, it's a parallelogram. And if we get onto the TV here where I have the microscope focused up, there's a whole bunch of those guys stuck together. And you'll notice, especially right down in the corner here, look at the little parallelogram shaped guy. Now this is in the microscope, so that's super tiny. Here's another one right here. You can see the edge on it. So the key to a crystal is its shape. Now, even if it's really, really small, it's still going to have the same shape as one that's really, really big. And the shape of the crystal is determined by the shape of the molecule that the crystal is made of. So if you all want to go back in time to last night, I know I was outside last night and listening to the spring birdies chirping when suddenly it started to snow, which is pretty typical of western Pennsylvania in spring. You never know what you're going to get. And snow, as a lot of you know, is water that's solidified. So it's just water molecules that are frozen. Snowflakes are actually crystals of water, or ice crystals. And water, as we know, is the molecule H2. These are my two white balls, or the H2, hydrogen, and O, oxygen. So two hydrogen atoms, one oxygen atom makes a water molecule. And you see the shape there. Actually, a lot of people joke around and say it kind of looks like a little Mickey Mouse. The shape of this molecule is why snowflakes have the shape that they do. We're going to set this up on the table so you can all see it. Now, those of you that have participated in Outside the Box Labs after school programs will know we always bring up magnetism in, wow, probably more than half of the activities that we talk about. And we know that opposites attract. We're talking about magnetism. The opposite ends of magnets, north and south, south and north, will attract, while the same will repel. Same thing works with molecules. A lot of molecules interact with each other magnetically. And in a water molecule, the oxygen tends to have a negative electromagnetic charge, whereas these little hydrogens are positive. So the oxygen with the negative is always attracted to the positive of hydrogen. And when we have liquid water that gets cold enough to freeze, they start to stick to each other magnetically, with the opposites attracting one another. And due to the shape of a water molecule, they line up in these cool six-sided hexagons. And you can see here, we've got negative oxygen to its opposite positive hydrogen. Opposites attract, opposites attract. And then now we have some positives sticking out here, so other molecules will stick opposite to opposite again. And you see what's happening here. We're starting to get the shape of a snowflake out there. And that's why snowflakes have six sides. That's why they have these little branches. You can put another water molecule here. You can put ones off of that. You get those little needles, but it's always six-sided snowflakes. And it's because of the shape of the water molecule and where the magnetic charges are. So all of these different substances that we're going to work with tonight, and if you don't have them all, it doesn't matter. Use whatever you have. But whatever you do have is going to crystallize based on the shape of the molecule we're working with. And again, it happens magnetically. These molecules act with one another just as if they were little tiny magnets. I'm going to throw another slide in the microscope. This is one of the materials that you might be using tonight. Get that thing in focus. And there's some little crystals right there. Let's zoom around here for a second, see if we can't find some really good ones right over here. All right, and if you look at these crystals, they're really small. Again, pretty much all the same shape. And the shapes we're seeing are cubes, little four-sided figures. These are salt molecules that have crystallized, or sodium chloride is the molecule. And this is what a sodium chloride molecule looks like. The sodium atom, chlorine atom stuck together. Now, again, if we go opposites attract, sodium is positive, chlorine is negative. They're going to line up opposite to opposite, like that. And then if we add some more, let's go opposite to opposite, and opposite to opposite, and they start to stack. And you'll notice there we have made, I put them together wrong. Opposites attract. Opposites attract, Talman. We have a little cube there, which is like what we're looking at there, only instead of this being made of just 4 molecules, these are made of millions and millions of molecules, even though they're very tiny. So a crystal made of 4 molecules is still going to be the same shape as a crystal made of 4 million molecules or a crystal made of 10 billion molecules. That's the cool thing about crystals. Now, in order to get our crystals to line up in this sweet pattern, we have to make the molecules free to move. That's what we're going to be working on tonight. And it's actually very simple to get the molecules free to move. Think about our snowflake example. Liquid water, a liquid is very free to move. I just stuck my hand in some water, it drips, it swirls around. So if you have something that melts and then cools slowly, it'll crystallize. There's another item that's in the DIY Sci Kit. If you get your little baggie of gallium out of there and melt it in your hand and then let it cool down really slowly in the open air, that will actually crystallize. Gallium crystals are really cool looking. And the cool thing about that is you can always melt them down again and make new crystals. This is what our copper sulfate molecule looks like. Imagine how complicated those stack up. I'm not even going to try it because it's got a lot going on. But these were what we looked at, the blue crystals earlier. That's this blue powder. How do you make those molecules free to move around and stack with each other when they're in these little kind of powdery pellets inside here? Well, the key here, instead of melting, is going to be we're going to dissolve it. And that's where your water is going to come in. Now, my water is warm. It's not boiling hot or anything. You don't want to use boiling hot water because that's a hazard. You can burn yourself. Hot tap water is more than sufficient. So I'm going to make 2 of these at once. And I'm going to make the copper sulfate crystals just because they're cool. But I'm also going to make some with table sugar. And these are the ones that you can eat. You can make rock candy out of this. And rock candy is just crystallized sucrose, which is the chemical name for table sugar. And sucrose crystals not only look really cool, they taste really good. So I'm going to make 2 different types while you're working along at home. But you can make one and then go back and watch again. Maybe you don't have all this stuff and you want to try it later when you do get a different type of molecule. So work at your own speed here. I'm going to try and go nice and slow so you keep up. So we need to take the molecules that make this, in this case copper sulfate and table sugar, free to move around. And instead of melting this like we did with our snowflakes, we're going to dissolve it in water. So we want to add quite a bit. And the key here is to get as much dissolved in that water as you possibly can. And when the water will not take any more of the solid and dissolve it, we say we've made a solution that is saturated. Saturated means full. So to get it to dissolve, you dump the powder in and you stir it up. And the molecules separate from one another and start sticking to the water molecules. You'll know you've saturated your solution when you start seeing solid sitting on the bottom that won't dissolve. So I'm going to go ahead and start one here too with the sugar. I'm going to add kind of a lot to this because water can dissolve quite a bit of sugar. And again, you're going to want to go ahead and take a spoon. You have a plastic spoon, even a metal spoon. I'm using a little wooden stir stick. Whatever you have, go ahead and stir that up. Now, one question that's brought up quite often to me about this is, well, what happens if we put 2 or 3 different chemicals in together? I want you to think about that. It's a lot harder for the molecules to line up in that repeating pattern if there are different shaped molecules in the way. Remember, the shape of the molecule and the way they're attracted to one another is what makes our crystals shape the way they are. And the shape of a crystal is what makes a crystal different from something that is not a crystal. So if you have 2 completely different shaped molecules, say you have copper sulfate and sodium chloride, they don't really stack very nice. Now, I have seen some students experiment with it just because they were curious, and they've gotten some really interesting results. Seems like they get different results every time. I've seen dozens of different combinations. I've seen dozens of different answers. So if you want to experiment, go right on ahead. That is how we learn stuff. That's what science really is. Testing things, seeing what happens, and answering questions. We're going to continue to go on here and try to saturate our solution. This is my sugar solution. And you want to stir as much as you can. Just keep on stirring until it won't take any more. I've probably added just about enough to my sugar or sucrose solution. I'm going to go ahead and saturate up my copper sulfate solution now. Stirring it up. I can still see some swirling around at the bottom, but it looks like it's still dissolving. I haven't quite saturated it yet.
Yeah, and really the best way to tell that you've saturated it thoroughly is if there's a little bit on the bottom that just is not going into that solution, because that means that that water can't hold any more of those molecules and it is completely saturated. So if you have a little sediment after you've been stirring for several minutes, that's probably an indication that you're there.
That's when you're there. And it doesn't hurt to add a little bit too much. You can always pour the liquid off the top to get it out of there. I thought this was saturated. It still isn't. Actually, my sugar one here is pretty much saturated now. And I'm going to bring that closer so you can see what we're talking about. See, so I still have some solid sugar down here at the bottom. I could probably keep on stirring, and some of that might go into solution. Some more might dissolve, but it looks like we've pretty much hit the peak of what we can get to dissolve. You see down there, I still have a good bit of sugar down there. Don't be afraid to stir longer than I have, though. Just in the interest of time, I'm going to go ahead and move on to the next step with both of these. So now you have your molecules, and they're dissolved in water, so they're all free to move around and rearrange themselves. The problem is, well, now they're kind of liquid, and they won't crystallize like that. Now we have to get rid of the water and let those molecules stack up with one another. And this is where you're going to have to be a little bit patient. The best way to get rid of the water is to let it evaporate slowly. Now, I had a gentleman at one of the schools around here raise his hand. He said, well, could we boil the water? Because that would make it evaporate real fast. Really good question. The problem there is when you boil the water, bubbling and churning, and if you've ever seen a pot of boiling water, it's steaming and bubbling and splattering everywhere. That makes it a little too difficult for the molecules to line up against one another because they're constantly moving. There's too much energy in there swirling them around. So boiling doesn't really make good crystals. The best way to make good crystals is to let the water evaporate nice and slow. And the more surface area or the more spread out your water is, the faster it will evaporate. Now, there's a catch here. If you have a big, flat, thin layer of water, your crystals are only going to be as tall as the liquid is deep. But if you have, I could leave this whole thing out and just let it evaporate slowly and get big monster crystals in there, but it might take maybe 2 or 3 weeks for all that water to evaporate. So this is where you're going to have to make up your mind. Do you want crystals in 2 days? Or do you want really big crystals in 2 weeks?
Well, and actually, if anybody has a dehumidifier, because we live in Pittsburgh and there's been a lot of rain, and a lot of people have basements, you can set that next to that dehumidifier. That will definitely expedite the process of evaporation for you.
The key is you want to put it somewhere nice and still. So don't put it on a dehumidifier. Right, if it's vibrating, put it near the dehumidifier.
Right next to it.
So you're going to want to put these somewhere the cat isn't going to get it, somewhere maybe your little baby brother or sister isn't going to get into it, especially something like this. That probably looks delicious, but it's pretty toxic. You don't want to drink this stuff. Copper is not good for you. And keep it out of the way. Don't let the cat get into it. Again, baby brother, sister, whoever, don't put it on top of the refrigerator where it turns on and it buzzes and vibrates. It'll shake your stuff up and your crystals won't look as nice. But again, key here is experiment. If you don't get the results you were expecting the first time, try it again and do something a little different. Maybe you didn't add enough of your chemical to your water. Maybe you had too much water. Change some things. Now, you don't need as much water as I have, but I'm only going to pour a small amount of this out. I'm going to put it in my Petri dish, but if you don't have a Petri dish, you can use a plate. You can leave it in the glass that you stirred it in. You can put it in a plastic cup. You can put it in a plastic bowl or a bowl of any type. It does not matter. The key is, do you want it to spread out and evaporate fast, or do you want to have big monster crystals that take a while? I'm going to make mine faster. So I'm going to pour some of my liquid out into the Petri dish in a nice thin layer. And I'm just going to take it over to the shelf here, and I'm going to let it sit downstairs in our basement isolation lab. And I'm just let time going to do its thing. I'm just going to let that liquid evaporate and let that stuff crystallize. And you will notice crystals in it as soon as a day or two. As some water starts to evaporate out of there, you will see crystals probably right away. They'll start really small, and as time goes on, they'll get bigger and bigger as more and more molecules come and join the other ones and stick together. Now we're going to revisit our sugar solution. And this is the one I said, if you're using table sugar or sucrose, you can actually eat this one when you're done. Not often that we get to eat our science projects, so we're going to take advantage of this one opportunity. I'm going to give you one cool option here. Not something you have to do, but something you can do if you want. Add a couple drops of food coloring to your rock candy or sucrose sugar crystals, and you can change their color. Now, some of you might be asking, doesn't the molecule of the food coloring get in the way of the crystals forming? Not really. This really won't cause much of a problem because these molecules are fairly small, I believe. I'm going to have to look into that, but I know it works. I've done it before. So I'm just going to stir my coloring in there. My solution is definitely saturated because I still have little pieces of sugar down there. And what I'm going to do is, and you don't have to do this, one way to make the rock candy, like the way you buy it in the store on a stick, is simply put a stick in there while it evaporates. And the molecules will be attracted to the stick to start with, and they'll begin crystallizing right there on the stick. Another way to do it is to take a little piece of string, and you can tie a knot, you can wrap it in a circle, you can tape it on, but put it around your stick and just kind of dangle it down in there, and the crystals will form along the length of your string. And then you'll have kind of like a rock candy necklace or bracelet, depending on how much string you used. Now, I made mine a little too long, so I just wrapped it along my stick to make it shorter, but it doesn't really matter. It can dangle all the way to the bottom. And then we're going to set this one aside to crystallize as well. Now, before we wrap up here this evening, I do want to show you all something that I think is really cool. We were talking about how molecules are sort of electromagnetic. They're attracted to each other based on electromagnetic ideas. Opposites attract, positive is attracted to negative, negative is attracted to positive. I'm going to do a little demonstration here to leave you that will sort of prove that. I still have my copper sulfate solution, what's left of it, and where else do you see that plus and minus or positive and negative symbol? On a battery. So I'm going to plunk my battery behind here. I'm going to hook a couple wires up, one to the positive, one to the negative, and you should see these molecules attracted to the electrical charges if we drop these two wires down into our solution. Usually it happens pretty quickly too. This is another way to make crystals, and I'm going to see if I can fish out my example that I have for you all of an electrochemical copper crystal that I made. These guys can get really big, actually. Bring these over to the camera.
Sing it.
Get it into the light or hold it. This is a pair of giant copper crystals that I made using electricity. And the copper in this blue copper sulfate, copper atoms were attracted to the negative side of my battery and started to form. And actually, if you look down in here, we can see it happening. See if I can lift this up. You'll see my one electrode is bubbling here on the one side. And my other electrode is actually starting to collect. See how dark it got? It's starting to collect copper. And if I leave that in there for overnight, hours, I'll end up getting really big copper crystals like that one I just made. I'm actually putting that in there to add some more copper metal to it. And that kind of can be used as a way to prove that these molecules are attracted to positively charged and negatively charged items. So while you are letting your crystals dissolve over the next week, maybe get online and take a look at some of this. There are a lot of different chemicals that you can make electrocrystals with just by using a battery and what's left over of your solution and having the molecules attract to the positive or negative charges that the electricity generates. So again, we hope some of you will share some of your results and some of your ideas with us. If you have any questions, we'd absolutely love to hear them. There's a lot of information down in the description section about the Rube Goldberg Challenge and about where you can get some of the equipment that we used here tonight. Hope everyone's staying safe and exploring from home. We can't wait to see you all again in person when everything is safe to do so. We will see you again next week. Next week's topic is going to be thinking about doing a little something about stopping time next week and waves, but we'll get you information about that early next week. Thanks for coming in and have an awesome weekend. Bye, everybody.